Take the entire life of the universe, all of it, past and future, and squeeze it down into a single calendar year. On that calendar, every star that will ever burn, the whole age of light we live inside, is finished within the first few minutes after midnight on the 1st of January. Everything you think of as normal, warmth, sunlight, galaxies, a sky full of stars, all of it happens in those opening minutes. And then the rest of that year, day after day, month after month, is dark. We are not living in the middle of cosmic history. We are living in its first bright instant, and almost the entire calendar lies ahead of us, unlit. So what is the universe doing during all those dark months? And what happens after the last star dies? Get comfortable and settle in. Hit subscribe if this is your first time here, because by the end of this, you will have walked that whole dark calendar, era by era, and understood what becomes of a universe that can no longer make a single point of light. Now, let's gently fall into this. Part 1. The shortest chapter. The stars are temporary, every one of them, including the small yellow one that warms your face on a clear afternoon, is a passing thing, and the sky full of them, that you have quietly assumed is the permanent backdrop of reality, is closer to a single frame in a film that runs for longer than you have names for. We tend to think of the lit universe as the normal state of things. Stars burn, galaxies turn, light crosses the dark and lands on something, and this feels like simply how the universe is. Tonight I want to gently take that assumption apart, because the truth is almost the reverse. The universe that makes light is the exception, not the rule. The darkness is the rule, and we happen to have arrived during the brief, bright, crowded opening, while the lights are still on. Consider how old everything is right now. The universe is a little under 14 billion years old, and that already sits at the edge of what a human mind can really feel. 14 billion years is deep enough that the entire span of recorded human history disappears inside it without leaving a mark you could measure. But here is the part that reorders everything. 14 billion years is not the middle of the story. It is not even the early middle. On the timescale that actually governs the fate of the universe, we are still inside the first small fraction of the first chapter, standing in the earliest light, and almost the entire future is still ahead, running out into numbers so long that 14 billion years rounds down to nothing beside them. There is a way physicists talk about this that makes it manageable, and it comes from the work of two astrophysicists, Fred Adams and Gregory Laughlin, who in the late 1990s laid out the future of the universe as a sequence of enormous eras. They measure time, not in years, but in what they call cosmological decades, which is just a way of counting the zeros. Instead of writing out a number with 40 digits, you talk about the exponent, the power of 10. In that counting, the universe right now is early in the 10th cosmological decade, meaning its age is around 10 to the 10th power years. That framing sounds abstract until you see where it leads, because the eras that come after us are not measured in the 10th decade or the 20th. They run out to the 40th, the 100th, and far beyond, each one longer than everything that came before it combined. Adams and Laughlin divide the whole future into 5 great ages, and it is worth hearing them just as names first, because the shape of the list tells the story before any of the details do. There was the primordial era, the hot young universe cooling down and making its first particles. There is the stelliferous era, the age of stars, which is the one we live inside right now, the age of galaxies and sunlight and warmth. Then comes the degenerate era, the age of stellar corpses. After that, the black hole era, when black holes are the only large things left. And finally the dark era, a universe of near-perfect cold and stillness that stretches on with no obvious end. We live in the second of 5, and the second is by far the shortest. It helps to slow down on what a cosmological decade really means. because it is the tool that makes the rest of tonight thinkable. Each cosmological decade is not one step larger than the one before it. It is 10 times larger. Moving from the 10th decade to the 11th does not add 10 billion years. It adds 90 billion, because you are multiplying, not adding. By the time you reach the 40th decade, each single step forward is longer than a trillion times the present age of the universe. This is why the eras stack the way they do, each one swallowing everything before it. Our whole history so far, every star that has ever burned, sits down in the low decades, near the front. The degenerate era does not begin until around the 15th decade and runs to the 39th. The black hole era stretches from the 40th out toward the 100th, and the dark era begins past the 100th and simply keeps going. Laid out that way, the shape of the future is not a line with us in the middle. It is a line with everything we know crushed into the first small segment, and an almost limitless dark stretching out to the right, decade after decade after decade, each one dwarfing all the rest. One way to feel the imbalance is to imagine shrinking the entire life of the universe, past and future, down to a single year. On that calendar, the hot early universe and the first stars flare up in the opening moments of the first day of January. Our own time, this present moment, is also still in that first day. The last stars finish burning. The entire age of light, all of it is over, within the first few minutes past midnight on the 1st of January. And then the rest of the year, every day from January onward, through the following December and far, far beyond, because a single year comes nowhere close, and we would need year after year after year. All of that is dark. The proportions really are that severe. The light does not get the first month, or the first week, or even the first day. It gets the first few minutes, and everything after is the long, dark remainder. That is the timeline we are about to walk, and we are standing, right now, in those first bright minutes. That word, shortest, is the one to hold on to, because it is where intuition breaks. The age of stars feels endless to us. It has already lasted billions of years, and it will last for a very long time yet. But set it against what follows, and it collapses into a sliver. The stelliferous era, the entire span in which the universe contains shining stars, runs to about 100 trillion years. That is a long time. And yet the degenerate era that follows it runs 1,000 trillion times longer than that, and the black hole era longer again, out past a number written as 1, followed by 100 zeros. If you compress the whole history of the universe into a single day, all of the starlight, every galaxy that has ever shone or ever will, would be finished in the first tiny fraction of the first second, and the rest of that day, hour after hour after hour, would be dark. This is the quiet reversal I want to sit with before we go anywhere else. You have most likely carried a picture of cosmic time, in which the stars are the setting, the stage that everything happens on, and the far future is some strange epilogue tacked on at the end. The real proportions are the other way around. The darkness is the stage. The stars are the event. The lit universe is a short, warm, improbable flash near the very beginning, and everything we have ever seen or loved or looked up at belongs to that flash. We are not living in the universe's long middle age. We are living in its first morning, in the narrow window when there is still light to see by. And that raises the question this whole video is built around, the one I am going to walk towards slowly and answer plainly only at the very end. If the age of stars is a brief opening, then what comes after it? What actually happens to the universe once the last star has burned out and the lights go off for good? Not in a poetic sense, but physically, concretely. What does a universe do when it can no longer make light? What is still there? What is still happening? And how long does it go on? By the end of tonight, you will have walked the entire timeline, era by era, out to the strangest and last events physics can currently name. and you will understand exactly what happens after the last star dies. But we cannot start at the end. We have to start where the light begins to fail, and that failure begins, gently, with the sky we have right now. Part 2. The long afternoon of the stars. The dimming has already begun, though it is far too slow for any human to notice. Star formation across the universe peaked billions of years ago, in an epoch astronomers sometimes call cosmic noon, and it has been declining ever since. The gas that stars are built from is being used up and locked away inside the remnants of dead stars faster than it is being returned, and so, generation by generation, the universe is building fewer new stars than it did before. We are already past the brightest hour. The cosmos is in its long afternoon, and the light is beginning, imperceptibly, to lengthen and redden toward evening. To see how firmly this decline is already underway, it helps to know that the universe was once far more fertile than it is now. Several billion years ago, in the epoch astronomers call cosmic noon, galaxies were forming stars many times faster than they do today, blazing with new light across the sky. Since then, the rate has been falling steadily, and it is still falling. The reason is simply supply. Stars form from clouds of gas, and every time a generation of stars is born, some of that gas is locked away permanently inside long-lived dwarfs and dead remnants that will never give it back. The cosmic supply of fresh star-making gas is being spent and not replaced, and the accelerating expansion is pulling the remaining reservoirs apart before they can gather. Run that forward, and the conclusion is unavoidable. The universe will keep making stars for a long time yet, but each era will make fewer than the last, from redder and smaller material, until the gas is either used up or scattered too thin to collapse at all. We are not watching a cosmos in its prime building phase. We are watching one that has already spent most of its star-making budget, coasting on what is left. Layered on top of that fading fertility is the steady work of the expansion, and it does something almost eerie to the night sky over the coming eras. As the space between galaxies stretches faster and faster, the galaxies that are not bound to us are carried away, and their light, already faint, is stretched toward the red and dimmed further, until each one fades past the point where any instrument could ever recover it. This does not happen all at once. It happens galaxy by galaxy, the most distant ones slipping away first, the nearer ones following, the sky slowly emptying from the outside in. 100 billion years from now, an astronomer in our merged galaxy could point the finest telescope imaginable at the darkness between the stars and find nothing there at all. No other galaxies, no structure, no sign that the wider universe had ever been full of light. The cosmos will have drawn a curtain around every island of stars, and each island will be left believing, with no way to know otherwise, that it is all there is. The emptiness of the far future does not arrive with the death of the stars. It arrives long before, as the expansion quietly carries almost everything out of sight. Follow that afternoon forward, and the first thing that happens is close to home. In about 5 billion years, our own sun will run out of the hydrogen in its core, swell into a red giant large enough to swallow the inner planets, shed its outer layers, and settle down as a white dwarf, a dense, cooling ember about the size of the Earth. Around the same time, on a similar timescale of 4 to 5 billion years, the Milky Way will collide with its large neighbor, the Andromeda Galaxy. The two spirals will pass through each other, tear at each other with gravity, and eventually merge into a single rounded elliptical galaxy that astronomers have half-seriously nicknamed Milkomeda. Almost no stars will actually strike one another in that collision, because the distances between stars are so large, but the shape of our galactic home will be rebuilt into something new. Then something stranger begins, and it has to do with the darkness itself expanding. The universe is not merely large, it is growing, and that growth is speeding up, driven by whatever it is we call dark energy. Over roughly the next 100 billion years, That accelerating expansion will carry every galaxy that is not gravitationally bound to us away and outward, faster and faster, until each one crosses a kind of cosmic horizon and its light can no longer reach us at all. One by one, the galaxies beyond our own small bound group will redden, dim, and slip out of view for good. 100 billion years from now, an observer in Milkomeda who looks out at the sky will see essentially one galaxy, their own, floating in a darkness that reaches in every direction with nothing in it. I want you to feel how disorienting that particular fact is, because it changes what knowledge itself will be possible. Everything we have learned about the universe being born, about it expanding, about the other galaxies rushing away, we learned by looking out and seeing those other galaxies and measuring their light. A civilization that arises late enough, after the expansion has emptied the sky, would look out and see only their own island of stars in an ocean of black, and they would have no way to discover that any of the rest of it had ever existed. The evidence will have receded beyond reach. The universe is quietly deleting the record of its own origins, and it will finish deleting it long before the stars themselves go out. Now let me take you into that late afternoon, so it is not just numbers. Imagine you are standing on the surface of a rocky world very far in the future, deep enough into the age of stars that most of them are already gone. Above you hangs the star this world circles, and it is not a fierce white or yellow sun like ours. It is small and dull and red, a coal rather than a flame, giving off a thin, tired light, and very little heat. You could very nearly look straight at it. The ground under your feet is cold, and when you lift your eyes past that red star to the rest of the sky, there is nothing there. No band of a home galaxy across the black, no other galaxies, no scattered brilliance, just this one small red ember, and beyond it, in every direction, an unbroken dark that goes on without a single other light in it. This is not a dead universe yet. That red star is still burning, still holding a world. But it is one of the last of its kind, and the emptiness around it is what most of cosmic time actually looks like. That small red star matters more than its dimness suggests, because stars like it are what the age of stars finally comes down to. The most massive stars, the brilliant blue ones, live fast and die young, burning through their fuel in only a few million years. Stars like our Sun last for roughly 10 billion years. But the smallest stars, the red dwarfs, are misers. A red dwarf with less than a tenth of the Sun's mass burns its hydrogen so slowly and stirs its fuel so thoroughly that it can keep going not for billions of years, but for trillions. The smallest of them can shine for more than 10 trillion years, nearly 1,000 times longer than our Sun will manage, sipping their fuel the entire time. They are the long, low, banked coals of the universe, and they are the ones that will still be burning when everything brighter has long since gone dark. So the age of stars does not end with a bang or a sudden darkness. It ends the way a fire ends, with the bright flames gone first, and a few stubborn embers glowing on far longer than seems possible. The last stars in the universe will be these red dwarfs, and they will keep their small worlds dimly lit for an almost incomprehensible stretch after the last bright star has died. But even a miser's fire runs out eventually. The fuel is finite, and so there is a moment, far out at the end of the long afternoon, when the very last of these embers begins to gutter. What happens in that moment, when the final star in the entire universe starts to go out, is where the light itself comes to an end. Part 3. The sky goes out. There is a last star. Sit with that phrase for a moment, because it is stranger and heavier than it first sounds. Somewhere far in the future, there is a single star that will be the final one still burning, the last object in the entire universe running on nuclear fusion, and there is a moment when its light goes out and is never replaced by anything. Before that moment, the universe, however dim, is still a place that makes light. After it, the universe is dark for the rest of time, That threshold has a rough address on the timeline. The age of stars, the whole stelliferous era, ends at around 100 trillion years after the beginning, which is the point where the last and smallest red dwarfs finally exhaust the last of their fuel. Understanding what actually happens to that last star means understanding why it dies at all, and the answer is almost tender in its simplicity. A star shines because it is fusing light elements into heavier ones in its core, and that fusion pushes outward, holding the star up against the crush of its own gravity. As long as there is fuel, the star holds. When the fuel runs low, the outward push weakens, and gravity, which never tires and never stops, begins to win. For the smallest red dwarfs, there is no dramatic finish. They do not explode. They do not swell into giants. They simply cool and contract and fade, their fusion sputtering out, until what remains is a dim, dense, slowly cooling remnant, a small ball of exhausted matter that will never shine again. The last star does not go out with a flourish. It goes out like a held breath being let go. It is worth being clear about why the smallest stars die so gently, because it is the opposite of the violent deaths that get all the attention. A massive star dies in a supernova because it builds up a heavy core it cannot support and collapses catastrophically. A star like the Sun dies more mildly, swelling and shedding its outer layers. But the smallest red dwarfs do neither. They are so thoroughly mixed inside, churning like a slowly boiling pot, that they burn nearly all of their fuel rather than just the fraction near the center, and they never build up the kind of unstable heavy core that leads to a dramatic end. So when a red dwarf finally runs low, it does not explode and it does not swell. It simply dims. Its fusion slows and then stops, and it settles into a cooling remnant, a small dense body that will never shine again. That is why the last star in the universe will almost certainly be one of these, and why the final end of starlight will not be a bright catastrophe, but a quiet fading, the smallest and most patient kind of star, simply running out and going dark. Let yourself feel the full oddness of a last star, because it is a genuinely new kind of thing to contemplate. For as long as there have been humans, and for billions of years before that, the sky has always had stars in it. Starlight is the one constant we never think to question, the background against which everything else has happened. It was there before life, before the earth, before the sun, and we simply assume it will always be there in some form. But it will not. There is a final one. There is a specific star, somewhere in the far future, that will be the last to shine, and a specific stretch of time, during which its light dims and goes out, and after which the sky is dark and stays dark for the entire remaining history of the universe. No new star ever forms again. The background constant of all existence switches off. It is not a violent ending, and not a frightening one, but it is a profound one, the closing of the only chapter of cosmic history that contains light, and it happens so early in the whole span of time that almost the entire life of the universe takes place afterward, in the dark that the last star leaves behind. Let me slow all the way down here, because this is one of the moments in the whole story that deserves it. Picture the final star in the universe, in its last age of light. It is a red dwarf, small and cool, and it has been burning for trillions of years already, longer than the entire prior history of stars that came before it. Around it, the sky is absolute black, no other star anywhere, no galaxy, nothing but this one small red glow, and the dark. On whatever cold worlds still circle it, its light falls thin and reddish across frozen ground. And then, slowly, over a span of time longer than the current age of the universe, that red glow begins to deepen and dim. The star is not dying in an instant. It is fading, like the last coal in a hearth, going from red to a dull, sullen glow, to something you can barely see, and then, at last, to nothing at all. There is no one to watch it. There is no final flash to mark it. There is simply a last star, and then a universe in which every star has gone out, and the darkness that follows has no end. That is the true weight of the last star, and it is not a weight of fear. It is the recognition that starlight, the thing we have always treated as the fixed background of existence, the given, the thing that was there before us and will be there after us, actually has a final performance. There is a last time the universe makes light. Every sunrise you have ever seen, every star anyone has ever wished on, every photograph of a galaxy, all of it belongs to a chapter with a closing line. The light is not forever. It is a phase, and the phase ends here, at around 100 trillion years, when the last ember gutters out and is not replaced. And yet, and this is the crucial turn, the story does not end when the light does. This is the mistake almost everyone makes about the end of the universe. We imagine that when the stars go out, that is the end, the credits, the final page. But the death of the last star is not the end of the universe. It is barely the end of the beginning. Remember the proportions from earlier. The entire age of stars, everything up to and including this last gutter of red light, fills only the thinnest sliver of cosmic time. When the last star dies at 100 trillion years, the universe is not finishing. It is a newborn that has only just opened its eyes. Almost the entire future, era upon era of it, is still to come, and all of it happens in the dark. So what is left, once the light is gone? That is the real question. And it turns out the answer is not nothing, far from it. The universe after the last star is not empty. It is full of objects, strange, cold, dense, invisible objects, the corpses and remnants of everything that used to shine, and they do not simply sit there. They cool, they crystallize, they collide, they slowly come apart, and over spans of time that make the age of stars look like an eye blink, they carry the universe forward through chapter after chapter of a history almost no one ever thinks about. The first of those chapters is the longest era of stellar corpses, a period the physicists call the degenerate era, and it begins the moment the light goes out. To understand it, we have to learn what a dead star actually becomes. Part 4. The Era of Embers. A dead star does not disappear. That is the first thing to understand about the age that follows the light, and it quietly overturns the picture most of us carry. When we imagine a universe with no more stars, we tend to imagine a universe with nothing in it, a clean emptiness. But the death of a star is not a vanishing, it is a transformation. Every star that has ever lived leaves a corpse behind, a dense knot of exhausted matter, and once the last star dies, the universe becomes a place absolutely full of these corpses, drifting and cooling in the dark. The physicists call this stretch of time the degenerate era, and it is populated by the remains of everything that used to shine. To walk through it, we need to know what those remains actually are. When a star like the Sun dies, what it leaves behind is a white dwarf, and a white dwarf is one of the strangest objects in ordinary physics. Take the mass of a star, more than the mass of our Sun, and pack it into a ball roughly the size of the Earth. The matter inside is crushed so tightly that a single spoonful of it would weigh as much as a small truck. It does not collapse further only because of a quantum rule, a kind of stubbornness, written into the electrons themselves, which refuse to be squeezed past a certain point. This stubbornness is called degeneracy pressure, and it is what gives the whole era its name. A white dwarf is not held up by fire, the way a living star is. Its fire is out. It is held up by pure quantum defiance, and it will hold that shape, essentially, forever. That quantum defiance is worth pausing on, because it is one of the quiet marvels of physics, and it governs the whole age of embers. The rule behind it is that certain particles, electrons among them, refuse to occupy the same state as one another. You cannot pile them into the same place with the same motion, no matter how hard you push. In an ordinary object, this rule is invisible. But squeeze matter hard enough, as gravity does inside a dead star, and the electrons get packed so tightly that this refusal becomes a genuine outward force, a pressure that has nothing to do with heat and does not fade as the object cools. This is degeneracy pressure, and it is what lets a white dwarf hold up the mass of a star in a body the size of a planet without any fire inside it. It is a fundamentally different way for an object to exist. A living star is a balance between the outward push of fusion and the inward pull of gravity, a balance that must end the moment the fuel runs out. A white dwarf is a balance between gravity and a rule of quantum mechanics, and that rule never runs out. The neutron stars take this same principle one step further and make it more extreme still. When a star too massive to end as a white dwarf collapses, the pressure becomes so overwhelming that the electrons are crushed into the protons, turning them into neutrons, and it is now the neutrons that refuse to be packed together, holding the object up by the same quantum stubbornness at a far higher density. The result is a body with more mass than the Sun compressed into a sphere the size of a city, so dense that a single sugar cube of its material would weigh about as much as a mountain. These two persist into the age of embers, cold and spinning and silent. So the degenerate era is furnished with a whole family of these quantum-supported corpses, white dwarfs and neutron stars, and the failed stars called brown dwarfs, each one a different way for matter to sit in the dark, holding its shape without any fire, each one waiting out the enormous span of the era on the strength of a rule rather than the strength of a flame. When a heavier star dies, it leaves something even more extreme. Stars considerably more massive than the Sun end their lives in a collapse so violent that the electrons are driven into the protons, and what remains is a neutron star, an object with more mass than the Sun, compressed into a sphere only a dozen or so kilometers across, the size of a city. A neutron star is so dense that its material is nearly the density of an atomic nucleus, as if you had taken an entire star and squeezed it until it became one enormous atomic core. And scattered among these are the brown dwarfs, the failed stars, objects that never had quite enough mass to ignite proper fusion, and which have been sitting in the dark the whole time as cool, dim balls of hydrogen, waiting. Once the true stars are gone, these corpses and near misses are what the universe is made of. But the corpses do not stay warm. A white dwarf begins its afterlife glowing faintly, still radiating the leftover heat of the star it used to be, a fading warmth with no new fire behind it. Over enormous spans of time, it cools, and as it cools, something quietly beautiful happens inside it. The carbon and oxygen that make up its body, under that crushing pressure, begin to arrange themselves into an ordered lattice. The interior crystallizes. The dead star turns, slowly, from the inside out, into a single planet-sized crystal, a sphere of what is essentially diamond with the mass of a star. When it has finally cooled all the way down, when the last of its inherited heat has drained away and it glows no more, it becomes what physicists call a black dwarf, a cold, dark, crystalline corpse that gives off no light at all. Let me take you close to one of these, because it is one of the things I most want you to be able to see. Imagine you are drifting through the dark of the degenerate era, and ahead of you is a black dwarf, the cold remnant of a star that once shone like our sun. You cannot see it. It emits no light, no warmth, nothing for an eye to catch. You only know it is there because the few far-off embers behind it wink out as it passes in front of them, and because you feel the faint pull of its gravity as you approach. When you finally reach it, you are looking at a sphere about the size of the Earth, perfectly dark, and inside that sphere, invisible in the black, is a single crystal, an ordered lattice of carbon that is, in the most literal sense, a diamond with the mass of a star. It is denser than anything you have ever touched. It gives nothing back. It just drifts there, cold and silent and enormous. One grave among countless graves, and the universe is full of them, spread out across distances so large that each one is utterly alone. That is the character of the Age of Embers. The universe is not empty. It is a field of invisible diamond corpses and city-sized neutron stars and dark failed stars, all cooling toward the same final cold, spread across distances so enormous that each object is essentially alone in its own pocket of dark. There is almost no light. Once in a very long while, something happens to break the black. Two brown dwarfs, drifting for ages, might finally collide, and their combined mass could be just enough to reignite fusion, lighting a small new star that burns for a while before it too dies. In the crowded cores of old galaxies, dead stars sometimes collide and flare. But these are rare sparks in an overwhelming darkness, brief and scattered, the last uncommon flames in a universe made of embers. And I want you to hold that word, embers, because it is going to come back. Right now, the embers are the cooling corpses of stars, fading slowly toward black, and they seem like the quiet end of things. But one of them, far down the timeline, is going to do something no one would expect an ember to do. We are not ready for that yet. For now, the embers cool, and the degenerate era, this age of dark and drifting corpses, is not a brief intermission before the real end. It is one of the longest chapters in the entire history of the universe, running from around 1,000 trillion years after the beginning out to something like 10 to the 39th power years. A stretch so long that the entire age of stars that came before it is less than a rounding error against it. For almost all of that time, nothing much happens. The corpses cool, the dark deepens. But the objects in the degenerate era are not truly at rest, even when they seem to be, and neither are the structures they belong to. The universe at this stage is still organized. The dead stars are not scattered randomly. They are still gathered into galaxies, the same enormous gravitational families they belonged to when they were alive, wheeling slowly around their centers in the dark. A galaxy full of black dwarfs and neutron stars is still a galaxy, still bound, still turning. It has simply gone out, like a city, after every light in every window has been switched off, but the streets are all still there. For a long time, those dark galaxies hold their shape. But gravity, over long enough spans, does not only hold things together. Given enough time, it also takes them apart. And the next thing that happens to the universe after the last star dies is that the galaxies themselves begin, slowly, to come undone. Part 5. The Unraveling of the Galaxies. Gravity is patient, and patience, over the timescales we are now entering, is a kind of solvent. We usually think of gravity as the force that assembles things, that pulls matter together into stars and worlds and galaxies and holds them there. And it does. But inside a galaxy, gravity is not a single steady pull. It is a churning field of countless individual tugs, every dead star pulling on every other as they pass and swing around one another in the dark. Over ordinary timescales, those tugs average out, and the galaxy simply turns. But over the almost limitless time of the degenerate era, those small encounters, slowly, relentlessly, rearrange everything, and the galaxy begins to take itself apart. The process is called gravitational evaporation, and the name is well chosen, because it works very much like the way a warm liquid loses molecules from its surface. Every so often, two dead stars pass close enough to swing sharply around each other, and in that encounter, one of them gets flung outward, picking up speed at the expense of the other, which sinks deeper toward the galactic center. Do this a few times, and nothing changes. Do it for 10 to the 19th or 10 to the 20th power years, encounter after encounter after encounter, and the consequences become total. The comparison to evaporation is more than a loose figure of speech, because the underlying mathematics really is the same as a warm liquid losing molecules from its surface. In a glass of water, a few molecules near the surface by random chance, end up moving fast enough to escape into the air, and they carry energy away with them, and over time the water level drops. In a galaxy of dead stars, a few remnants, by the random chance of their gravitational encounters, end up moving fast enough to escape the galaxy's pull, and they fly off into intergalactic space, carrying energy away, and over time the galaxy thins out. Physicists even have a name for the characteristic time this takes, the relaxation time. And for a galaxy, it is enormous, but not endless. Run the process across 10 to the 19th or 10 to the 20th power years, and a galaxy does not merely lose a few stars, it comes apart almost entirely. The great majority of its remnants are flung out into the growing dark, each one launched onto a lonely trajectory that will never bring it near another object again. It is worth holding this against the thread we keep returning to, because it deepens the reversal at the center of tonight. We think of a galaxy as one of the permanent furnishings of reality, a fixed island of stars that simply exists. But a galaxy is not so much a thing as a temporary arrangement, a crowd of objects held loosely together for a while, and like any crowd, it eventually disperses. In the lit era, we see galaxies at the height of their gathering, bright and full and turning. What we do not see, because we arrived so early, is that this gathered state is itself a passing phase. After the last star dies, the dark galaxies hold their shape for a long time, but not forever, and then they come apart, and the very concept of a galaxy stops applying to the universe. One more familiar feature of the cosmos, one more thing we assumed was simply the way things are, turns out to belong only to the brief, bright chapter we happen to inhabit. Structure itself, like light itself, is temporary. Most of the dead stars, most of the black dwarfs and neutron stars in the galaxy, are gradually kicked out entirely, flung away from their old home into the growing emptiness between galaxies, each one sent off alone into the dark. And a minority, the ones that keep sinking inward instead of being thrown out, spiral down toward the very center, where something is waiting for them. What is waiting at the center is a black hole, and not a small one. At the heart of essentially every large galaxy, including our own, sits a supermassive black hole, a black hole with the mass of millions or even billions of suns. Right now, these central black holes are relatively quiet, but across the unraveling of the degenerate era, as dead stars spiral inward, the central black hole feeds, swallowing the remnants that fall toward it, and growing more massive with each one it takes. So the dark galaxy meets a twofold fate. Most of its corpses are scattered outward into isolation, and the rest are drawn inward and consumed by the growing black hole at its heart. Either way, the galaxy as a structure ceases to exist. The great gravitational family comes apart, its members either exiled into the dark or absorbed into the maw at the center. I want to connect this back to the thread we have been following, because it is easy to lose the human scale in numbers this large. Everything we have ever meant by the word galaxy, the glowing pinwheels in every telescope image, the Milky Way arching over a dark landscape, the sense that stars belong to great collective structures, all of that is a feature of the lit era and the era just after it. It does not last. Given enough time, the galaxies do not merely go dark, they come apart, until there is no such thing as a galaxy anymore, only isolated dead objects, drifting incredibly far from one another, and the central black holes left behind, where the hearts of galaxies used to be. The universe is not only losing its light across these eras, it is losing its structure, its organization, the very idea of things being gathered together. And remember what dark energy is doing the whole time this unfolds. While each galaxy is coming apart from the inside through gravitational evaporation, the accelerating expansion of the universe is carrying whatever is left further and further from everything else. The two processes work in the same direction, toward isolation. A dead star flung out of an evaporating galaxy does not drift into some new neighborhood. It drifts into an emptiness, that is itself growing, stretching, pulling every distant thing even further out of reach. By the late degenerate era, the universe is a place of almost unimaginable loneliness. Individual cold remnants and growing black holes, each one separated from the next by distances that only ever increase, in a darkness with no edges and no other lights. It would be reasonable to think, at this point, that we have reached the true end. The stars are gone. The galaxies have come apart. What is left is dark, cold, scattered, and still. Surely this is the final state, the quiet forever. But it is not. And the reason it is not takes us into one of the most unsettling ideas in all of physics, an idea that reaches down past stars and galaxies and even past the death of light, all the way down to the matter itself. Because everything we have talked about so far, the white dwarfs, the neutron stars, the black dwarfs, the diamond corpses, all of it is made of atoms, and atoms are made of protons, and there is a serious, testable possibility, taken seriously by many physicists, that the proton itself is not permanent. That given enough time, matter does not merely cool and scatter, it dissolves. If that is true, then the corpses in the graveyard are not the end of the story either, because the graveyard itself is slowly evaporating, atom by atom, into nothing. Part 6. When matter itself forgets how to exist. The proton might be mortal. This is one of those sentences that sounds like a small technical footnote and is actually a trapdoor under everything you thought was solid. We tend to treat matter as the permanent thing, the stuff that lasts. Energy comes and goes, light fades, heat dissipates, but the atoms, we assume, endure. The carbon in a diamond, the iron in a core, the protons at the center of every atom in your body, these feel like the bedrock, the things that do not expire. And for almost all of practical experience, they do not. But according to a broad family of theories in particle physics, the proton is not truly stable. It is only very, very long-lived. And if that is right, then even the diamond corpses of dead stars have an expiration date. The theories that predict this are called grand unified theories, and they come out of the attempt to show that the different forces of nature were once a single unified force in the early universe. A recurring consequence of these theories is that the proton, which we normally treat as rock solid, can very occasionally decay, falling apart into lighter particles and radiation. The reason unification points toward a mortal proton is worth understanding, because it is not an arbitrary guess. In our everyday world, the particles that make up matter, the quarks inside protons, and the lighter particles like electrons seem to belong to completely separate families that never turn into one another. That is why the proton looks stable. There is simply no allowed way for it to fall apart. But the grand unified theories propose that at extremely high energies, the kind that filled the very early universe, those separate families were once a single family, governed by one force, able to transform into one another freely. If that is true, then the walls between the families are not perfectly solid even now. They are only very, very high, and once in a great while, a quark inside a proton can slip across, allowing the proton to decay. The first such theory, proposed in 1974 by the physicists Howard Georgi and Sheldon Glashow, made a specific prediction for how long this would take, and remarkably, that first prediction was short enough that experiments could test it and rule it out, because the proton lived longer than that simplest theory allowed. That is why the great tanks of water were built and are still watched. Each passing year, without a single proton death, pushes the true lifetime higher and rules out more versions of the theory, narrowing in on the answer one patient year at a time. There is a quiet vertigo in this that is easy to walk past, so let me make it plain. Everything you think of as solid, the floor, the chair, your own hands, is made overwhelmingly of protons and neutrons, and we tend to treat those as the permanent bedrock beneath all the changeable things. Cells die and are replaced. Objects wear away. but the underlying particles, we assume, simply endure. Proton decay, if it is real, says otherwise. It says that solidity itself is temporary, that the particles at the base of all ordinary matter have a finish line, and that given enough time, everything made of them, every atom that ever belonged to a world or a star or a living body, dissolves back into radiation and a thin drift of lighter particles. The reason this does not alarm us in daily life is only the size of the timescale, a number with more than 30 zeros, so long that in the entire age of the universe, almost no proton should yet have died. But out in the deep degenerate era, that number is not the far future, it is the present, and matter itself reaches the end of its life. The bedrock, it turns out, is not bedrock. It is just very, very slow. The predicted lifetime is not short. It is somewhere around 10 to the 34th to 10 to the 37th power years, a number so large that in the entire history of the universe so far, essentially no protons should have decayed at all. But the timescales we are now walking through are longer even than that. In the deep degenerate era, 10 to the 37th power years is not the far future, it is the neighborhood. And on that clock, proton decay stops being a rare curiosity and becomes the thing that dismantles all ordinary matter. Here is the remarkable part. We are not merely speculating about this from theory. Right now, today, human beings are actively watching for proton decay, and have been for decades. Deep under a mountain in Japan sits one of the most patient experiments ever built, and I want to take you inside it, because it is happening in our own time. Go down, a kilometer beneath the peak of a mountain, into a chamber carved out of solid rock. In front of you is an enormous stainless steel tank holding 50,000 tons of the purest water on Earth. Water so clean, it is almost eerie to look at. Lining the walls, floor to ceiling, are more than 11,000 golden glass eyes, sensitive light detectors called photomultiplier tubes, each one staring inward at the water, waiting. The whole cavern is silent and dark and cold. And the reason this machine exists, the thing all of those thousands of eyes are watching for, is a single flash. If even one proton, among the unthinkable number of them in all that water, happens to decay, it will throw off a faint ring of light, and these detectors will catch it. Scientists have staked entire careers on sitting in the dark and waiting for one proton out of all that water to die. So far, they have not seen it. And that fact is itself precious data, because the experiment has watched so much water for so long without catching a single clean proton death. It has been able to prove that if the proton decays at all, its lifetime must be enormous, longer than about 2 times 10 to the 34th power years for the most searched for kind of decay. We do not yet know whether the proton truly dies. We only know that if it does so with almost incomprehensible patience. But notice what that means for our story. Even the shortest lifetimes the experiments still allow are exactly the timescales of the deep degenerate era. If the proton is mortal at all, then somewhere out there, in that long darkness, the matter of the universe begins, quietly, to come apart. And when it does, the dead stars themselves become the stage for it. Picture a black dwarf, that cold diamond corpse, sitting in the dark, 10 to the 37th power, years after the beginning. Inside it, one by one, protons begin to decay. Each decay releases a tiny bit of energy, a small flicker of radiation deep inside the crystal. There are so many protons that these flickers, added up, give the black dwarf a faint internal warmth, and it begins to glow, ever so slightly, not from fusion, not from leftover heat, but purely from its own matter falling apart inside it. A dead star at this stage would radiate at only a few hundred watts, less than the light bulbs in a single room, its entire enormous body glowing as dimly as a handful of bulbs, powered by the slow dissolution of its own protons. And as this goes on, the black dwarf slowly loses mass, shrinking, evaporating from the inside, until, over spans reaching toward 10 to the 40th power years, it is essentially gone, converted into radiation and a thin drift of lighter particles. This is the quiet, devastating end of the degenerate era. It is not just the stars that end, and not just the galaxies. If the proton decays, then ordinary matter itself has a finish line. Every white dwarf, every neutron star, every diamond corpse, every atom that was ever part of a world, or a star, or a body, slowly dissolves back into radiation and stray particles, until there is no ordinary matter left in the universe at all. And I want to bring that all the way home, because it is not only about distant dead stars. The protons in the theories that might decay are the same protons that are in you, right now, at the center of every atom in your hands, your bones, your blood. If those theories are right, then the matter you are made of does not last forever. Not chemically, not biologically, but at the deepest level, the level of the particles themselves. The stuff of you has an expiration date written into it, out past a number of years, with more than 30 zeros. When the last of the ordinary matter has dissolved, the universe has crossed another threshold. There are no more stars. There have not been for an almost limitless time. There are no more galaxies. And now there is no more ordinary matter of any kind. No atoms, no diamonds, no corpses. And yet, astonishingly, the universe is still not finished, because there is one kind of object that does not decay along with everything else. One kind of thing that survives the death of matter itself and inherits the dark universe for the next enormous chapter. Those are the black holes, and their age is the strangest yet. Part 7. The Age of Black Holes. The black holes inherit the universe. Once the last star has died, and the galaxies have come apart, and even the atoms themselves have dissolved away through the slow decay of their protons, the only large objects left in the entire cosmos are black holes. They were there all along, of course, waiting quietly at the centers of galaxies and scattered through space as the corpses of the most massive stars. But now they are alone. Everything else is gone. The universe has entered what the physicists call the black hole era, a chapter in which these are the only significant structures anywhere, and it is by far the longest and emptiest age we have yet reached. To understand it, we have to confront something that sounds like a contradiction, because it turns out that black holes, the objects famous for letting nothing escape, are themselves slowly dying. For most of the history of physics, a black hole was understood as a perfect trap. Its gravity is so extreme that beyond a certain boundary, the event horizon, nothing can get out. Not matter, not light, not information, nothing. By that logic, a black hole should last forever, or at least should only ever grow, swallowing whatever falls in and never giving anything back. But in the 1970s, a piece of physics emerged that changed the picture completely, and it came from putting quantum mechanics and gravity together at the very edge of the horizon. The result is that a black hole is not perfectly black after all. It glows faintly with a kind of radiation that leaks away its mass over time. That glow is called Hawking radiation, and it means that black holes, given long enough, evaporate. The mechanism is subtle, but the consequence is what matters for us. Empty space, at the quantum level, is not truly empty. It constantly churns with pairs of particles flickering into and out of existence. Near the edge of a black hole, one of a pair can fall in while the other escapes, and the escaping particle carries away a tiny bit of the black hole's energy, and therefore a tiny bit of its mass. Bit by bit, particle by particle, the black hole leaks itself away into the surrounding dark. Stephen Hawking worked this out in the mid-1970s, and it was a genuine shock to physics, because it connected three things that had always seemed to belong to separate worlds. It tied gravity, described by Einstein's relativity, to quantum mechanics, the physics of the very small, and to thermodynamics, the physics of heat and entropy. A black hole, Hawking showed, is not just a gravitational object. It has a temperature, and it has an entropy, and it radiates like a warm body, however faintly. That single result told us that black holes are not eternal and not truly one way. They participate in the same slow accounting of energy and entropy as everything else in the universe. And the temperature it assigns them is the strange, backwards quantity we keep returning to. It depends on nothing about what fell into the black hole, not what kind of matter, not what history, only on its mass. A more massive black hole is a colder one. A less massive black hole is a hotter one. What makes this genuinely disorienting is that it gives a black hole, of all things, a temperature you could in principle write on a thermometer, even though a black hole is a region where matter and light have fallen in and cannot come back. The temperature does not belong to anything inside. It belongs to the horizon itself, to the boundary, and it is set by how sharply space-time is curved there. For any black hole heavier than a mountain, that temperature is so far below the cold of empty space that it rounds to nothing, and this is exactly why the whole black hole era has to wait. As long as the universe around them is warmer than they are, black holes take in more than they give off and cannot begin to truly shrink. Only after unimaginable spans of expansion, once the leftover warmth of the cosmos has drained below even the black hole's own faint temperature, does the balance finally tip, and the long, slow dying can begin in earnest. The largest black holes are the coldest, so they are the last to reach that tipping point, and the last to finish. It is an almost unimaginably slow process, slower than nearly anything else in nature, but it never stops, and over the timescales of the black hole era, slow and unstoppable is all it takes. There is a strange and important twist in how this works, and it runs exactly opposite to intuition. You would expect a bigger black hole to radiate faster and die sooner, the way a bigger fire burns more fiercely. In fact, it is the reverse. The temperature of a black hole's glow is inversely related to its mass. The bigger the black hole, the colder it is, and the more slowly it radiates. A small black hole is relatively hot and evaporates comparatively quickly. An enormous one is unbelievably cold and evaporates with almost infinite patience. This inversion is the key to the whole era, because it means the biggest black holes, the supermassive ones, left over from the hearts of dead galaxies, are the coldest, the slowest, and the very last things to go. That coldness is so extreme, it explains a puzzle about why this era has to wait so long to even begin in earnest. A black hole with the mass of our sun has a temperature of about 60 billionths of a degree above absolute zero. That is far colder than the universe is now. Right now, all of space is bathed in a faint afterglow left over from the early universe, a background warmth of about 2.5 degrees above absolute zero. Compared to a black hole, that background is warm, and this creates a curious situation. A black hole colder than the space around it actually absorbs more warmth from that background than it radiates away, and so, at present, black holes are not really evaporating at all. They are still very slightly gaining. Only after the universe has expanded and cooled for an enormous span, until the background warmth finally drops below even the black hole's own faint temperature, can they truly begin to net evaporate. The black hole era proper has to wait for the rest of the universe to grow colder than the black holes themselves. Try for a moment to simply sit inside the patience of this era, because there is a strange calm in it once the numbers stop frightening you. Picture a single black hole, somewhere in that long dark, radiating so slowly that across a span of time longer than the entire age of the universe so far, it has barely changed at all. There is no light near it. There is no warmth, no motion, no other object within any distance that would mean anything. There is only this one dark shape, curving the space around it, giving off a trickle of radiation so faint it would take instruments we cannot imagine even to detect, and it will go on like that. unchanged to any watching eye, not for millions of years or billions, but for a length of time with dozens of zeros after it, a stillness so prolonged that the whole bright history of stars and worlds and life is less than a single flicker at its very start. Nothing hurries here, nothing arrives. The black hole simply persists and radiates and waits, and the universe holds its breath around it for a span that has no comparison in anything we know. It is the longest, quietest patience there has ever been, and it is most of what the future actually is. Once that threshold is crossed, the long dying begins, and the timescales are where the mind simply has to let go of ordinary comparison. The rate of evaporation depends on the cube of the black hole's mass, which means larger black holes do not last a little longer, they last overwhelmingly longer. A black hole with the mass of a star takes something like 10 to the 64th to 10 to the 67th power years to fully evaporate. Write that out, and it is a 1 followed by 60-odd zeros, a span against which the entire prior history of the universe, stars, and galaxies, and the whole long degenerate era is a vanishing instant. And that is only for a modest, star-sized black hole. The supermassive ones take almost incomparably longer. Consider one of the true giants, a black hole with the mass of 100 billion suns, the kind that once sat at the center of a large galaxy. Its temperature is so close to absolute zero that the word cold does not really apply anymore. Its evaporation, its trickle of Hawking radiation into the surrounding black, is so slow that it will keep going for about 2 times 10 to the 100th power years. That number, 10 to the 100th power, has a name. It is called a googol, a 1 with 100 zeros after it, and it is the kind of number that was invented essentially as a joke about how large a number could be. And here it is, describing a real physical process, the patient death of the largest black holes, ticking away, one faint particle at a time, across a googol years of darkness. So the black hole era is an almost inconceivable expanse of near-nothingness. The universe is dark, empty, and cold beyond any cold we can name. Scattered through it, separated by distances that only ever grow, are the black holes, each one radiating its faint glow into the dark, each one shrinking by the most imperceptible degree, on its way to an ending that lies a googol years off. For essentially all of this era, nothing happens that a watcher could see. There is only the slow, silent leaking away of the last great objects in the universe. And yet each of those black holes is genuinely dying, counting down, and each one, at the very end of its countdown, does something that after all this darkness is almost violent. Because a black hole's death, when it finally comes, is not a fade, it is a flare. Part 8. The last light a black hole ever makes. A black hole ends by getting hotter. This is the final, counterintuitive turn of the whole process, and it follows directly from that backwards relationship between mass and temperature. As a black hole radiates and loses mass, it gets smaller. And because smaller means hotter, losing mass makes it radiate faster, which makes it lose mass faster still, which makes it hotter again. The process feeds on itself. For almost the entire life of a black hole, this runaway is nowhere in sight, because the black hole is so large and so cold that its shrinking is imperceptible. But every black hole eventually reaches a point, very near its end, where it has lost so much mass that the feedback becomes fierce. In the final stretch, the black hole heats up rapidly, its faint glow climbing through the spectrum, growing brighter and more energetic as it shrinks. The last portion of its mass, which took most of the black hole's enormous lifetime to whittle down to, evaporates in a comparatively brief and furious finale, releasing a burst of high-energy radiation and a spray of exotic particles, everything the laws of physics allow to be made from raw energy, flung outward all at once. The amount of energy released in that final burst is considerable by any human measure, comparable to an enormous explosion. But it happens in a universe so empty and so spread out that there is nothing anywhere near it for it to affect. It simply expands into the dark and thins away. There is something worth pausing on in the fact that these final bursts are, quite literally, among the last things that will ever happen in the universe. For almost the entire black hole era, nothing occurs that could even be called an event, only the imperceptible leaking of radiation into the dark. The evaporation bursts are the exceptions, the rare punctuation marks near the end of the era, each one the death of a black hole that had waited out spans of time longer than the whole prior history of the cosmos. And because the largest black holes are the last to go, the final such burst, the death of the single most massive black hole in the universe, is one of the last genuine events of any kind that the universe will ever stage. After it, there are no more objects left to do anything. The universe crosses from a place where things, however rarely, still happen, into a place where nothing happens ever again. That final black hole burst is, in a real sense, the universe's last word, spoken into a dark that has no one in it to hear. For almost the entire life of the black hole, across all those inconceivable spans, the evaporation is slower than slow, a trickle so faint it is barely there. But right at the very end, when the black hole has shrunk down to its last tiny fraction, the whole thing accelerates catastrophically, and the black hole finishes not with a whisper, but with a burst, a final flare of radiation and high-energy particles thrown out into the dark as the last of its mass converts to energy all at once. Let me bring you to one of these endings, because after so much darkness, it is worth witnessing. Imagine you are present near one of the last black holes in the universe, unthinkably far down the timeline, near a googol, years after the beginning. For its entire existence, this black hole has done almost nothing. It has sat in a darkness so complete and a cold so total that there has been nothing to mark the passage of time at all. Leaking radiation, so faint that across spans longer than you can hold in your mind, it barely changed. It is the last large object of any kind anywhere in the universe. And now, at last, it is reaching the end of its evaporation. It begins to shrink faster. It begins, impossibly, to warm. The faint trickle becomes a stream, then a flood. And in its final moment, after a googol years of near-perfect silence, the last black hole in the universe detonates, blazing out in a burst of particles and radiation, a single flare of light and energy, into an emptiness that has known nothing but dark for longer than there are words for, and then it is gone, and there is nothing large left in the universe at all. That flare is a genuinely strange thing to think about, because it is one of the last real events the universe will ever stage, and there is no one and nothing to receive it. It happens in an emptiness so complete that the burst simply expands outward into the dark and disperses, its energy spreading thinner and thinner across the growing void, never landing on anything, never seen. And with the death of the last black hole, the universe crosses the final great threshold of structure. Before it, there were still objects, the black holes, the last things holding any concentration of mass and energy together. After it, there are no objects at all, no stars, gone for an eternity, no galaxies, no matter, and now, no black holes either. The age of the black holes, the longest chapter yet, is over, and what follows is the strangest and emptiest condition the universe can be in. But before we step across that last threshold, I have to be honest with you about a fork in the road. Because the timeline I have just walked you through, the one that ends with the black holes as the final objects, depends on something we do not actually know for certain. It depends on the proton decaying. Remember that back in the degenerate era, the reason the dead stars dissolved, the reason matter itself came apart and left the black holes alone to inherit the universe, was that the protons inside all that matter slowly fell apart. That is the mainstream expectation, and it gives us the clean sequence. the dissolving of matter, followed by the long age of black holes. But the experiments under the mountain have not actually caught a proton dying. It is entirely possible that the proton is truly, perfectly stable, that it never decays at all. And if that is the case, then the story of the universe after the last star dies goes very differently, and it leads to something even stranger than a black hole's final flare. Because if the proton never decays, then the dead stars never dissolve. The black dwarfs, those cold diamond corpses, do not slowly evaporate away in the degenerate era. They persist. They just sit there, in the dark, crystalline, and cold, and intact, for spans of time that make even the black hole era look brief. And you might think that persisting, that simply enduring in the cold forever, would be the quietest possible fate, an object doing nothing at all for an endless stretch of time. But it is not quite nothing, because even in a cold, dead crystal sitting in the dark, at the level of the individual atoms, something almost imperceptibly slow is still happening. And given enough time, and in this branch of the story there is more time than in any other, that slow something builds toward one of the most surprising events in the entire future of the universe. The dead stars, the frozen embers, are going to explode. Part 9. The supernovae no one will see. The embers are not as dead as they look. I told you that word would come back, and here it is, at the far end of one of the two possible futures. If the proton is stable, if matter does not dissolve, then the black dwarfs endure, and inside each one, buried in that crushing cold and pressure, an incredibly slow process continues to run. It is a form of fusion, but not the fierce, heat-driven fusion that powers a living star. It is something far quieter, called pycnonuclear fusion, fusion driven not by temperature, but by sheer pressure, and by the strange rules of quantum mechanics, and it works on timescales that make the age of stars look like a single afternoon. Here is what is happening inside a black dwarf. The atomic nuclei are locked into that crystal lattice, held rigidly in place, each one sitting a fixed distance from its neighbors. Normally, two nuclei cannot fuse unless they are slammed together with enormous energy, because they both carry positive charge and violently repel each other. In the cold heart of a black dwarf, there is no such energy. But quantum mechanics allows something that ordinary physics forbids. A nucleus does not have a perfectly fixed position. It has a slight fuzziness, a probability of being found a little to one side or the other, and very, very rarely, two neighboring nuclei can quantum tunnel right through the barrier between them and fuse, without ever having the energy that classical physics would demand. Each such event is almost unimaginably rare, but there are enormous numbers of nuclei, and there is enormous amounts of time, and rare multiplied by long enough becomes inevitable. The end point of all that slow fusion is iron, and there is a reason iron, and nothing heavier. Iron sits at the very bottom of the nuclear energy well, the most tightly bound of all nuclei, the ash left when fusion can release no more energy. So as the black dwarf tunnels its way forward, across almost endless time, its interior creeps toward iron and stops there, building up a growing core of the most stable matter there is. And here is the twist Kaplan identified. The maximum mass a dead star can hold up with its quantum pressure, the famous limit named after the physicist Chandrasekhar, is not a fixed number. It depends on the mix of particles inside, and as the black dwarf converts to iron, that limit slowly falls. For most black dwarfs, the limit never falls below their actual mass, and nothing happens. They simply become cold iron and sit forever. But for the heaviest black dwarfs, the ones that began above roughly 1.2 times the mass of our Sun, the falling limit eventually drops beneath their own weight, and at that point, their quantum pressure can no longer hold them. They collapse, and collapsing, they detonate. Kaplan calculated that the most massive of these would go first, around 10 to the 1100th power years from now, while the least massive to explode would not go until something like 10 to the 32,000th power years, a number so long the digits alone would fill a page. Roughly 1% of all the stars that exist, something like 1 billion trillion of them, would eventually meet this end. What stays with me about these last supernovae is not the physics, but the loneliness of them, and it deserves a moment. A supernova today is the most brilliant event a galaxy can produce, briefly outshining billions of stars, seen across enormous distances, studied and photographed and marveled at. A black dwarf supernova, out at the end of one branch of the future, would be every bit as bright, an enormous release of light and energy, and yet it would detonate into a universe that has been perfectly dark for longer than any number we have a real feeling for, with no stars anywhere, no worlds, no eyes, nothing whatsoever to receive it. The last light the universe ever makes would fall on nothing. It would expand outward into the dark, dimming, spreading, and simply fade, unseen and unrecorded, the final flare of the final ember, in a cosmos that had forgotten what light was. It is the loneliest event I can picture, and it is also, in a strange way, the most faithful. The universe, right to the very end of what it is capable of, keeps doing the one thing it did at the beginning. It makes light, one last time, whether or not anyone is there to see it. So across spans of time so long they defy any comparison we have used yet, the black dwarf slowly fuses its own interior, nucleus by nucleus, converting its carbon and oxygen, bit by bit, into heavier elements, and eventually toward iron, which is the most stable nucleus of all, the ash, at the end of every fusion road. The dead star is very slowly turning itself into iron from the inside out, and this is where a physicist named Matt Kaplan, in the year 2020, followed the logic to a genuinely astonishing conclusion. As the black dwarf converts to iron, its internal balance changes. The delicate quantum pressure that has been holding it up all this time depends on its composition, and as the composition shifts toward iron, the maximum mass that pressure can support slowly drops. For the most massive black dwarfs, the ones that started out heavier than about 1.2 times the mass of our Sun, that dropping limit eventually falls below their own mass, and when an object's own weight exceeds what its internal pressure can hold, it collapses. And when a stellar mass object collapses, it detonates. It becomes a supernova. Let me take you to that moment, because it may be the last light the universe ever makes. Imagine a black dwarf, 10 to the 1100th power years after the beginning of the universe. That number is so far beyond anything we have said so far that the earlier eras, the death of the stars, the age of black holes, all of it, is packed into the merest sliver at the very start of the time this object has been sitting here. The universe around it has been perfectly, absolutely dark for a span that has no meaningful comparison. There has been no light anywhere for longer than the mind can approach. And now, inside this frozen crystal corpse, the slow tunneling fusion finally tips the balance. The internal pressure loses its long fight. The black dwarf, cold and dark for an eternity, suddenly collapses in on itself, and in that collapse it ignites, detonating in a supernova, an actual burst of brilliant light and heat, and flung out matter, blazing into a universe that has not seen a single photon of starlight for an almost endless age. It is the first light in an eternity of dark, and it expands outward into the black, spreading, dimming, with no eye anywhere to catch it, no world to warm, no one to see that the universe, one final time, made light. There is something almost unbearably lonely and beautiful in that image, and it is worth sitting with, rather than rushing past. Kaplan calculated that these black dwarf supernovae, if the proton is indeed stable, would be the last events of their kind, and that roughly 1 billion trillion stars, something like 1% of all the stars that exist in the observable universe, would eventually end this way, each one detonating alone in the dark, across spans of time reaching from 10 to the 1100th power years outward to numbers with tens of thousands of digits. They are the universe's final fireworks, and the deepest strangeness of them is that they are a show with no audience. The last light the universe will ever make will fall on nothing and be seen by no one, flaring in a darkness that has already outlasted everything that could have watched. And this connects straight back to the thread we started with, the reversal that this entire journey has been circling. We think of light and life and warmth as the normal condition of the universe, and the darkness as the strange exception. But here, at the far end, is the truth of the proportions laid bare. The universe will spend so unimaginably long in the dark that even its final act of making light happens in a blackness beyond any measure, unwitnessed and alone. The supernovae no one will see are the last embers flaring one final time. But even they are not necessarily the true end, because there is a newer idea, only a few years old, that suggests the dead stars may not last long enough to detonate at all, that something dissolves them far sooner, and that nothing in the universe, not the black dwarfs, not the black holes, not even you, is truly permanent. Part 10. Even the corpses evaporate. Nothing is permanent, not the stars which we already knew, not the galaxies which come apart, not ordinary matter if the proton decays. And now, according to a piece of physics only a few years old, not even the objects we thought were the ultimate survivors, the black dwarfs and neutron stars and black holes themselves. In 2023, and then in more detail in 2025, a group of researchers at Radboud University in the Netherlands, Michael Wondrak, Walter van Soilekom, and Heino Falke, took another look at the physics behind Hawking radiation, and what they found quietly rewrites the last chapters of the story we have been telling. Recall how Hawking radiation was supposed to work. It happens at the event horizon of a black hole, that boundary of no return, where the extreme conditions let particles carry energy away. The event horizon seemed essential. It was the special feature that made black holes, and only black holes, capable of evaporating. But the Radboud group argued that the true driver of the effect is not the horizon itself, but the curvature of space-time, the bending of space and time by gravity, which is present around any concentration of mass, not only around black holes. If that is right, then the horizon is not required. Any object with enough gravity to curve the space around it should generate a similar kind of radiation, and should therefore, slowly, evaporate. Not just black holes, everything. The path to this conclusion ran through a specific and subtle piece of physics. And it is worth being precise about what the Radboud group actually did, because it is easy to overstate. They did not claim to overturn Hawking. They revisited the way empty space behaves near any strong gravitational field, using a framework physicists call vacuum polarization in curved spacetime. And they showed that the production of radiation does not strictly require the sharp boundary of an event horizon. The curvature of space around a dense body is, by their calculation, enough on its own to generate a slow leak of particles. In their first work, in 2023, they demonstrated the principle. In 2025, they extended it to real objects and calculated concrete lifetimes. The result was a dramatic shortening of the far future. In the older picture, the most durable objects, the black dwarfs, might have lasted until the almost unwritable timescales of the last supernovae. In the new picture, the most durable objects are white dwarfs, and they dissolve in about 10 to the 78th power years, which the researchers proposed, only half seriously, as a revised estimate for the effective end of the universe. That coincidence between the neutron star and the black hole, the two arriving at the same fate after the same span despite their wildly different gravity, is the kind of clue physicists take seriously, because clean coincidences in physics usually mean there is a deeper principle hiding underneath. It suggests that this curvature-driven evaporation depends on the overall mass and size of an object in a simpler way than anyone expected, in a way that does not care very much about whether there is a hard surface or an event horizon. Whether that hint leads somewhere real, we do not yet know. This is physics at the frontier, only a couple of years old, and it will take time and scrutiny from many other researchers before anyone can say whether it truly holds. But even as an unconfirmed possibility, it changes the emotional shape of the far future. In the classic timeline, there were candidates for near permanence, objects that might last almost unimaginably long. In this newer picture, that permanence quietly evaporates. There is no object anywhere, however dense, however durable, that simply gets to last. This is a genuinely unsettling idea, and it lands right at the heart of what we have been building, because it means the black dwarfs never get the chance to become supernovae after all. Long before 10 to the 1100th power years, long before the slow tunneling fusion could ever tip them into collapse, this curvature-driven radiation would have dissolved them. The researchers calculated the timescales, and they are, by the standards of everything else in this story, almost soon. A white dwarf, which turns out to be the most stubborn and long-lasting object of all under this process, would evaporate in about 10 to the 78th power years. That becomes, in this picture, a kind of true endpoint for the ordinary contents of the universe, and it is enormously sooner than the black dwarf supernovae would have arrived. The last corpses do not detonate in an almost endless future. They quietly radiate themselves away, much earlier, into the dark. Then came the detail that genuinely surprised the researchers themselves. When they calculated how long a neutron star would take to evaporate this way, and how long a stellar mass black hole would take, the two numbers came out essentially the same, around 10 to the 67th power years. That should not have happened, on the face of it. A black hole has far more extreme gravity than a neutron star. A true horizon, the most curved space-time there is. You would expect it to radiate faster and die sooner, but it does not. It comes out even with the neutron star. The reason, in their analysis, is that a black hole's lack of a surface changes how the radiation is produced in a way that exactly offsets its stronger gravity. So the two very different objects arrive at the same fate at the same time. It is the kind of coincidence that makes physicists lean in, because it hints at something deeper in the structure of the theory that we do not yet fully understand. And then the researchers did something that turned an abstract cosmological result into something personal, and I want to hand it to you exactly as they framed it, because it is the moment this whole subject stops being about distant dead stars and becomes about you. They asked how long it would take, by this same mechanism, for other things to evaporate. They calculated it for the moon, they calculated it for a human being, and the answer, for both the moon and a human body, came out to around 10 to the 90th power years. In principle, by the same physics that dissolves a black hole, you would slowly radiate away into nothing, particle by particle, given 10 to the 90th power years to do it. Now, of course, nothing survives remotely that long. A human body lasts a century at most, and would be dissolved by 1,000 other processes long before this one mattered. The number is not a practical prediction about a person, but that is not why it stops the breath. It stops the breath because of what it says about the kind of thing you are. It says that a human body and a black hole are, at the deepest level, the same sort of object, both of them concentrations of mass bending the space around them, both of them subject to the same slow leak back into radiation, both of them impermanent, in exactly the same way, and for exactly the same reason. The universe does not have one set of rules for its grandest objects, and another set for you. There is no category of thing that is exempt. Not the moon, not a diamond, not a black hole, not you. Everything with mass is slowly, in principle, evaporating. All of it on the same long clock, all of it made of the same impermanent stuff. all the way down. I find that, once the initial vertigo passes, strangely companionable rather than frightening. And I want to offer you that reading too. We spend a great deal of effort insisting on the difference between ourselves and the rest of the universe, between the living and the dead, the warm and the cold, the temporary and the lasting. And here is physics, at the end of time, quietly erasing the last of those lines. You are not a permanent exception standing apart from a decaying cosmos. You are made of the same thing as the last black holes, and you share their fate, and there is a kind of belonging in that, a sense of being woven into the same fabric as everything else, rather than set outside it. The stars are temporary. The black holes are temporary. You are temporary. It is all one kind of thing, briefly gathered into shape, on its way back to radiation. So whichever route the universe takes, whether matter decays through its protons, or the black dwarfs slowly radiate away, or, in the oldest and longest branch, a rare few of them detonate as the last supernovae, the destination is the same. The object's end, the concentrations of mass and energy that made stars and worlds and corpses and black holes all, eventually, come undone, dissolving back into the thinnest possible drift of particles and radiation, spread across a darkness that never stops growing. And when the last object of any kind is finally gone, the universe enters the condition it will remain in, as far as we can tell, for the rest of time. It is called the Dark Era, and it is the strangest state of all, because it is the one in which, at last, almost nothing ever happens again. Part 11. The Dark Era and the End of Events. The universe ends not with a collision, but with a stillness. After the last star, the last galaxy, the last atom, the last black hole, the last flare of the last dying object, what remains is the Dark Era, and it is less a place than a condition. There is no more structure anywhere. There are no objects. What is left is the thinnest imaginable fog of leftover particles, spread across a space that has expanded for so long and so far that the distances between them are beyond any description that would mean anything. A few stray photons of light, stretched by the endless expansion to wavelengths longer than we can picture, drifting with almost no energy at all. A scatter of neutrinos, those ghostly particles that barely interact with anything. And here and there, unthinkably far apart, a few surviving electrons and their antimatter partners, the positrons. That is the entire contents of the universe. That is what is left. And yet even here, in this almost perfect emptiness, physics does not quite stop, and one of the last things it does is strangely delicate. An electron and a positron, if they drift close enough, can capture one another into orbit, forming a bound pair called positronium, a tiny two-particle system that spins around its own center. This happens today, in laboratories, and the pairs are minuscule and vanish almost instantly. But in the Dark Era, where the particles are separated by almost inconceivable distances, an electron and a positron might find themselves loosely bound across a gulf larger than the entire observable universe is today, orbiting one another with agonizing slowness across spans of space and time that dwarf everything. These are the largest and most tenuous structures the universe will ever contain. Single pairs of particles held in orbits wider than everything we can now see, drifting through the dark. It is worth dwelling on how genuinely enormous and how genuinely slow these final structures are, because they stretch the meaning of the word object past anything familiar. A positronium pair in the Dark Era is not a tiny thing. The electron and positron can be bound across distances so large that the orbit encloses a volume greater than the entire universe we can currently observe, and they circle one another so slowly that a single orbit takes longer than the whole prior history of the cosmos. These are the loosest, faintest, most tenuous arrangements of matter that will ever exist, barely qualifying as structures at all, more like two lonely particles agreeing to drift in the same enormous circle, and their fate is annihilation. An electron and a positron are matter and antimatter, and when they finally spiral close enough, after spans that dwarf everything, they meet and destroy one another, converting entirely into a last flicker of radiation. The stillness that results is worth being precise about, because it is easy to picture it wrongly as an empty blackness and miss what is truly strange about it. The dark era is not empty in the sense of containing nothing. It contains energy, spread perfectly evenly, at a temperature just a hair above absolute zero, the same everywhere, forever. And it is that sameness, not the emptiness, that ends things. Everything that has ever happened in the universe, every star that burned, every thought that was thought, happened because energy was concentrated in one place and thin in another, and flowed between them. Heat death is the state where there is nowhere left for anything to flow, because everything is already the same. Physicists do allow one strange footnote here. In a universe sitting at equilibrium for endless time, random chance could, with almost impossibly tiny probability, briefly assemble a pocket of order out of the sameness, even, in principle, a fleeting arrangement that resembles a thinking observer. These are taken seriously enough to have a name and to be used as a check on our theories. But they are not a rescue. They are the rarest of accidents in an ocean of stillness, flickers of false order that dissolve as fast as they form, and they only underline how deep and how final the evenness has become. And slowly, over spans of time that make even the black hole era look brief, these pairs spiral inward and annihilate, each one a final, silent flicker as an electron and a positron meet and vanish into a last whisper of radiation. When even those are gone, the universe has reached the condition that 19th century physicists first glimpsed and named with a phrase that has haunted science ever since. They called it the heat death. It is the state of maximum entropy, of complete thermodynamic equilibrium, and it is worth being careful about what those words actually mean, because they are easy to misunderstand. Entropy is often described as disorder, but the truer meaning is evenness, sameness, the spreading out of energy until there are no differences left. A cup of hot coffee in a cool room has order, in a sense, a difference between hot and cold, and that difference can be used to do things, to drive a flow, to make something happen. As the coffee cools to room temperature, that difference disappears, the energy spreads out evenly, and nothing more can be driven by it. The heat death is that same process carried out on the entire universe. Every difference, every gradient, every concentration of energy that could ever be used to make something happen, gone. Everything the same temperature, a temperature almost exactly at absolute zero, everywhere, forever. The physicists who first understood this, in the 1800s, were shaken by it, and their names are worth saying, because they saw the end of the universe in the behavior of steam engines. Rudolf Clausius, who in 1865 coined the very word entropy, stated the whole thing in a single sentence that still stands, that the energy of the universe is constant, and the entropy of the universe tends toward a maximum. William Thomson, later Lord Kelvin, and Hermann von Helmholtz followed the same logic to the same cold conclusion. They realized that the second law of thermodynamics, the simple rule that heat flows from hot to cold and never the other way, when applied to the whole cosmos, pointed inexorably at a final state in which everything had run down, in which no energy could ever flow again, because there would be nowhere colder for it to flow to. They saw the heat death more than a century before we could fill in the eras that lead to it, and they were right. And this is where we finally arrive at the deepest strangeness of the end, the one that reaches past even the death of objects, because in true equilibrium, something happens to time itself. Think about how you know that time is passing. You know it because things change. The coffee cools, the light moves, the clock ticks, a thought follows another thought. Every marker of passing time is really a marker of some difference being erased, some energy flowing from a place that has more to a place that has less. But in the heat death, there are no differences left to erase. Nothing flows, because there is nowhere for anything to flow. Nothing changes, because every change has already happened. And a universe in which nothing changes is a universe in which there is no real way to tell that time is passing at all. The clock has not stopped. Exactly. It is that there is nothing left for a clock to measure. The arrow of time, the very sense of a before and an after, quietly loses its meaning, because meaning required difference, and difference is exactly what has run out. This is why it matters so much to separate two ideas that we usually let blur together: the end of the universe and the end of everything happening. The universe does not end in the dark era. It is still there. Space still exists, still expanding, still holding its thin drift of stretched-out photons and lonely particles. In that narrow sense, it goes on forever. What ends is not the universe. What ends is events. What ends is the possibility of anything ever happening again. And that, in the end, is the real answer hiding underneath the whole question of what comes after the stars. It is not fire, and not collision, and not a sudden nothing. It is a stillness so complete that it dissolves even the difference between one moment and the next. And so we come back, after this entire long walk through the dark, to the reversal we started with. And now you can feel it, rather than just hear it. The lit universe, the age of stars, the warmth and the structure and the constant happening of things, is the exception, not the rule. It is a brief disturbance, a short-lived unevenness, a fleeting period in which the energy of the cosmos was concentrated enough and uneven enough for things to occur, for stars to burn and worlds to form and events to unfold. The natural, default, overwhelmingly most common state of the universe is the stillness at the end, the smooth and even and eventless dark. We did not arrive in the middle of an endless day. We arrived during a brief flicker of activity near the very beginning, in the short window when the universe was still uneven enough to make things happen. And there is one last question worth asking before we let the dark have the final word, which is whether anything, any mind, any thought, any scrap of what we would call life could possibly hold on through all of this, and keep the happening going even as the universe runs down. Part 12. Could anything still be awake? Someone once tried to save the future. In 1979, the physicist Freeman Dyson wrote a paper with the quiet title, Time Without End, and he asked a question that no one of his stature had really taken seriously before. Could life survive forever? Not human life specifically, not bodies like ours, but life in the broadest possible sense. Any system that could gather energy, process information, think, remember, experience. Faced with the long cold running down of the universe, Dyson refused, at least on paper, to simply accept that everything must stop. He wanted to know whether intelligence, given enough ingenuity, could find a way to continue without end, even as the stars died and the energy thinned and the cold came on. His idea was patience carried to its ultimate extreme. As the universe cooled, Dyson reasoned, any surviving life would have less and less energy available to it, and so it would have to slow down to match. It would think more slowly, act more slowly, stretch each thought across longer and longer spans of time, and crucially, it would hibernate, running in brief bursts and then shutting down for enormous stretches to conserve energy, letting itself cool between thoughts. Dyson showed, with real mathematics, that a form of life, willing to slow down without limit and hibernate for ever longer intervals, could, in an open and steadily cooling universe, stretch a finite supply of energy across an infinite amount of time. It would never think a final thought. It would just think ever more slowly, forever. The elegance of Dyson's argument was that it did not require a mind to think faster or gather more. only to be endlessly patient and endlessly frugal. He drew a careful line between what he called subjective time, the number of thoughts a being actually experiences, and objective time, the years ticking by on a cosmic clock. His insight was that a being could keep its subjective time going without limit, experiencing an unbounded number of moments, even as each moment was stretched across ever longer stretches of objective time. It would spend most of eternity dormant, cooling, waiting, then rouse briefly to think a few more thoughts on a dwindling ration of energy, then sleep again for even longer. In Dyson's open, coasting universe, the sums worked. The total energy needed to think forever was finite, because each successive thought was allowed to cost less and take longer, and the shrinking costs added up to a finite total even across infinite time. It is worth honoring what Dyson was really doing, because it was not idle optimism. He was insisting that the question of meaning be treated as a physics question, that whether experience could continue was something you could actually calculate rather than merely feel hopeless about. And for a long while, his calculation gave a hopeful answer. It said that the running down of the universe, the very heat death that had troubled physics since the 1800s, might not be a wall after all, that a patient enough mind could keep having experiences without end, threading an endless number of moments through an endless amount of cooling time. Whether or not it turned out to be true, it was a profound reframing. The idea that the end of the universe is not necessarily the end of everything that matters, and that intelligence might be, in the deepest sense, unkillable. That is the hope the newer physics has had to test. It was a genuinely hopeful vision, a way for meaning to outlast the stars, and for a while it stood as a real answer to the heat death, a mathematical argument that the running down of the universe need not be the end of experience. But the universe, as we have learned it since, does not seem to allow even Dyson's patient dream. The problem is the very thing that has been shaping this whole story from the near future onward, the accelerating expansion driven by dark energy. Dyson worked out his argument for a universe that simply coasts and cools. He did not know, because no one knew until the end of the 1990s, that the expansion of the universe is speeding up. And an accelerating universe has a cruel feature. It has a horizon, a limit beyond which things recede too fast for their light or their influence ever to reach us, and that horizon puts a hard ceiling on how much energy and information any observer can ever gather, no matter how patient they are. In the year 2000, the physicists Lawrence Krauss and Glenn Starkman worked through what this does to Dyson's scheme, and the conclusion was stark. In a universe with dark energy, you cannot think forever. There is a finite total number of thoughts, a finite amount of information any being can ever process, even with infinite time and perfect patience, because the horizon starves them of the energy they would need. The slow, hibernating, eternal mind runs out after all. So the honest current answer to the question of whether anything could stay awake through the end is, most likely, no. Not because of a failure of cleverness, but because the structure of the universe itself, its expansion, its horizon, its relentless drive toward evenness, forecloses it. And yet, physics does not close the door completely, because physics is not finished, and it is important to be truthful about that. There are ideas, serious ones, that keep a narrow opening. One of them comes from the mathematician and physicist Roger Penrose, who noticed something almost poetic about that final state. In the far future, once everything has decayed to massless radiation, once there are no more particles with mass to serve as clocks or rulers, the universe loses any way to measure scale or time at all. And a universe with no way to measure size, Penrose argues, might become geometrically indistinguishable from the hot, dense, smooth conditions of a new beginning. The end, in this view, does not stay the end. It becomes, by losing all sense of scale, the seed of another beginning, another cycle, another age of stars far beyond our own. It is speculative, and it is contested, and it may well be wrong. But it means we cannot say with certainty that the story stops. We can only say that we do not know how it truly ends. Which brings us, at last, all the way back to the question we started with, the one I promised to answer plainly. What happens after the last star dies? Now you know. Almost everything happens after the last star dies. Almost all of time happens after the last star dies. The death of the last star, at around 100 trillion years, is not the end of the universe's story. It is barely the end of its opening line. After it come the diamond corpses cooling in the dark, and the slow unraveling of the galaxies, and the possible dissolving of matter itself, and the long age of black holes leaking away across a googol years, and the last unwitnessed supernovae, and the quiet evaporation of even the corpses, and finally the endless even stillness of the dark, in which time itself loses its meaning. What happens after the last star dies is nearly the entire history of the universe. The age of light, the age we live in, is only the brief, bright doorway at the very front of it. And that is the thought I want to leave with you, not as a weight, but almost as a gift. We are not living at the end of things, and we are not living in some tired late chapter of a universe winding down. We are living in the first, brief, brilliant flicker of light, in the narrow window, near the very beginning, when the universe is still uneven enough, still warm enough, still young enough, to make stars, and to make worlds, and to make minds, that can look up and wonder what comes next. Almost the whole future of the universe is darkness, but we did not arrive in the darkness. We arrived here, now, while the lights are still on, while the sky is still full, while there are still other galaxies to see, and other stars to name, and warmth on your face on a clear afternoon. That is not a small thing. Out of all the enormous stretch of cosmic time, nearly all of it dark and still and silent, we opened our eyes during the one short chapter that has light in it. The stars are temporary, the light is a phase, and we are here for it. Rest in that, tonight. The universe will have its long dark age, but not yet, not for a long, long time. Right now, the stars are still burning, and so are we.